There is a boundary to everything we see, not a wall, but a veil drawn by time itself. Beyond it, light has not yet arrived. Beyond it, causality unravels. Beyond it may lie the answer to the oldest questions humanity has ever asked. This is not a journey across space, it's a journey across time, a pursuit of the cosmic edge, the limits of the observable universe, and the tantalizing possibilities that exist beyond. This is not fantasy. It's not science fiction. It is physics, deep, elegant, and real. Welcome to Anantum and Beyond. We inhabit a planet just over 12,700 kilometers in diameter, orbiting a G2V class star at a distance of 149.6 million kilometers, a star we call the Sun. Our star resides in the Orion arm of the Milky Way galaxy, a spiral structure containing somewhere between 100 and 400 billion stars. But the Milky Way is merely one galaxy among billions. Our galaxy is gravitationally bound to Andromeda and dozens of smaller galaxies, forming the Local Group, a structure spanning 10 million light-years. Zoom out further, and we encounter the Virgo supercluster, a vast aggregation of galaxy clusters extending over 110 million light-years. But even this is not the end. The Virgo supercluster is just a branch of a greater structure, the Laniakea supercluster, encompassing over 100,000 galaxies, all flowing toward a gravitational anomaly we call the Great Attractor. All of this, from the Earth beneath our feet to the grandest galactic filaments, exists within a small fraction of what we can observe. We are embedded in a cosmic web, an intricate scaffolding of dark matter and luminous galaxies, extending for billions of light years. And yet, this is only the observable portion. At first glance, one might assume the observable universe should extend no farther than 13.8 billion light years, the time since the Big Bang multiplied by the speed of light. But reality, as is often the case in cosmology, defies simplicity. Due to the expansion of space itself, the true distance to the edge of the observable universe is closer to 46.5 billion light-years in every direction, creating a sphere roughly 93 billion light-years in diameter. How is this possible? The answer lies in the very nature of space-time. Light from distant galaxies has been traveling toward us for billions of years. Yes, but all the while, the space through which it travels has continued to stretch. By the time those photons arrive, the sources that emitted them have receded tens of billions of light years away. This is not motion through space, it is space itself expanding, a phenomenon described by Hubble's law, V equal to h naught into d, where v is the recession velocity, h naught is the Hubble constant, approximately 70 kilometers per megaparsec, and d the proper distance. At sufficient distances, v exceeds the speed of light, not violating relativity, but instead reflecting a deeper truth, that no signal can outrun the metric expansion of the universe. How fair is a clear, becoming a true, of universe we see is not the universe as it is now, but a fossil record, a layered time capsule where each photon tells the story of an ancient epoch. At the edges of visibility, we aren't looking across space, we're looking back into the infancy of time itself. As we look farther into space, we peer deeper into the past. But even light, the fastest thing in the known universe, is finite in its reach. At a certain distance, the expansion of space exceeds the velocity of light itself. Not because objects are traveling through space faster than light, but because the fabric of space is expanding faster than light can traverse it. This boundary is known as the cosmic event horizon. Roughly 16 billion light years from Earth lies a point of no return, not for us, but for the galaxies we observe. Anything currently beyond that horizon will never be able to send light to us in the future, not in a trillion years, not ever. Our sight, their signals are already causally disconnected from our future. This introduces a subtle but profound distinction. The observable universe is what we can see now. The event horizon defines what we can ever see, no matter how long we wait. And yet, this limit is not physical. No wall demarcates it. It is a boundary of information, dictated by the physics of space-time and the relentless march of cosmic acceleration. The culprit behind this accelerating expansion is a mysterious pressure permeating all of space, dark energy. Though it comprises nearly 70% of the energy density of the universe, we do not know what it is. We only know what it does. It drives galaxies apart, even as gravity tries to hold them together. The result is a future where most galaxies, perhaps all but the local group, will slip beyond our horizon forever. This is not speculation, it is observation, confirmed by redshift data, supernova measurements, and the cosmic microwave background. The edge of the visible universe is not the end of existence, it is the end of influence, the end of connection, a limit, not to what exists, but to what can ever matter. What lies beyond the observable universe? We don't know, and perhaps in principle we can't know. But based on what we do observe, we can infer, with caution and with awe. The standard cosmological model tells us that the universe is flat, not in 2 dimensions, but in its geometric curvature. Measurements from the Planck satellite show that if the universe is curved at all, it must be on scales larger than 10 to the power of 6 megaparsecs. So large, the curvature becomes undetectable. In simpler terms, space may be infinite. If that's true, then our observable universe is but a finite island in a sea of existence far beyond. And here modern cosmology touches something profound. According to the theory of cosmic inflation, the universe underwent a brief but exponential expansion, just 10 to the power of minus 36 seconds after the Big Bang. In that moment, space expanded faster than the speed of light by many orders of magnitude, smoothing out irregularities, solving the horizon problem, and seeding the structure we observe today. But inflation, according to many models, doesn't simply end everywhere at once. It ends locally, in patches. Each of these patches may stop inflating and form a universe like ours, while inflation continues elsewhere. This process, called eternal inflation, implies the creation of countless bubble universes, each born from a quantum fluctuation in the inflating field. Turn over this vast, possibly infinite landscape, the multiverse. Each bubble universe may carry its own laws of physics, different values of the fundamental constants, different particles, even different dimensions. Some might collapse instantly. Others may be lifeless, sterile voids. And in some, stars form, planets coalesce, and life, perhaps, arises. But for now it remains unobservable, not because it isn't real, but because it lies beyond what any light can carry, beyond what any signal could ever return. Even with our most powerful instruments, optical, radio, infrared, ultraviolet, our vision is still bound by light. Light has its limits. The most distant signal we can observe is the cosmic microwave background, a faint afterglow from a time just 380,000 years after the Big Bang. Before that moment, the universe was a dense, hot plasma, opaque to radiation, because photons scattered violently of free electrons in every direction. This epoch is known as recombination, when the universe cooled to roughly 3000 Kelvin, allowing protons and electrons to form neutral hydrogen. At that instant, the universe became transparent. Photons were finally free to travel without scattering. Those very same photons, stretched over billions of years into microwaves by cosmic expansion, are what we now detect as the CMB. The Planck and WMAP satellites have mapped this background to exquisite precision, revealing fluctuations on the order of 1 part in 100,000, the seeds of all structure we see today: galaxies, clusters, life. Yet, beyond this light, earlier than 380,000 years, the electromagnetic universe disappears. Our instruments, reliant on photons, are blind. We can theorize, model, and simulate the first instance of the cosmos, set up the quark-gluon plasma, band-center unification epoch, O'Brien behavior, even inflation itself. But we cannot observe them. Banking with photons of cosmos, we cannot observe this not in the cosmos. The limit is in our tools and in the very nature of light and time. To see beyond this wall, we must go beyond photons. Perhaps one day we will use neutrino telescopes or detect primordial gravitational waves, ripples from the Big Bang itself. But for now, the war remains. We ever reach the edge of the observable universe, or even travel beyond it with current technology? No. Even light, the fastest entity in existence, would take billions of years to cross a fraction of it, and yet itself recedes faster than light due to the expansion of space. But physics offers glimpses of escape routes, not easy ones and not proven, but routes permitted by the equations. One such concept is the Alcubierre drive, a solution to Einstein's field equations proposed in 1994. Rather than moving an object through space, it compresses space in front of the spacecraft and expands it behind, creating a warp bubble that carries the vessel faster than light without breaking local speed limits. This is not science fiction. The math is sound, but the cost is staggering. It would require negative energy density, exotic matter with properties not found in any non-material. Theoretical constructs, like Casimir vacuums, might help, but the engineering challenges are vast. Another proposal: wormholes. Theoretical bridges between distant regions of space-time. Originally predicted by Einstein and Rosen in 1935, these Einstein-Rosen bridges connect two points across vast distances, perhaps even different universes. But to remain stable and traversable, they too would require negative mass or exotic matter and be protected from quantum instability.
We think we are a bit of a science word, and I don't know what to explain in too well. Most Alcubierre standard over such those, like Einstein's Multiverse. With this age, we all command. General relativity allows them. Quantum mechanics makes them fragile and perhaps impossible. Still, these ideas hint at a deeper truth.
Nothing relativits lesse peplus fader and frandri, and betair area halts being oblight is long each, now care to get that important into them. Kind of relative per the prevelidis explains the kind, and I find them now speed of light is not the ultimate constraint. Mondrig is, geometry is, energy is. To break the boundaries of observation, we must first learn how to reshape the very fabric of space. Until then, we remain inside the cosmic bubble, dreamers, map makers, looking out from a shore we may never leave.
We began this journey at home, a pale blue dot adrift in a vast ocean of stars. We've traversed galaxies, horizons, and even the limits of light and time. But what lies at the edge of the universe may not be a location at all. It may be a boundary between what is known and what is forever unknowable. A wall of light, yes, but also a wall of understanding. The edge of the universe is not merely a distance. The general is a mirror, reflecting our curiosity, our boldness, and our humility. We may never reach the outer edge, but in trying, we expand a different frontier, one no telescope can measure, in the edge of human understanding. Thank you for watching Anantum Beyond. Subscribe to explore the deepest questions of space, time, and existence. Until next time, keep reaching.